Hi, welcome to this next video. In the previous video, we learned the physical or hardware side of computers. We understood that computer is a machine, in fact, a very intelligent machine. To think of it, intelligence is not built into the physical parts or hardware parts of the computer. Intelligence is built into the programs that we humans write and execute on computers. In this video, we will understand all about computer programs, softwares, and how it all connects to the physical world. So without wasting any more time, let us get started. In simple language, a software is something which runs on a computer and gets things done for us. But we will get to that step by step. To summarize from the previous video, at the physical level, a computer is a box made up of electronic components and electric current flows through it. However, intangibly, it is much more than that. This is where software comes in. A software is the intelligent brain behind the physical machine. To think of it, we have provided this brain to computers since it's us who build softwares. There is nothing a computer can do but we humans can't do. So it's the cognitive ability of humans that is somehow coded and executed in the form of a software on the physical computer hardware. Human brain is the center of intelligence, and human language is something by which we convey meaning, ideas, concepts to others. For any human language, a character is the minimal unit of text that has semantic value. So fundamentally, we should have some way to represent human language characters using computers. This is where character encoding comes in. Character encoding is the process of assigning numbers to graphical characters, allowing them to be stored, transmitted, or transformed using digital computers. Now you would ask, why assign integer numbers to characters? To think of it, a transistor can have two states. We can combine multiple transistors to have more possible states. In fact, we learned that the number of possible states can be specified as the power of 2. For simplicity, let us consider two transistors which can have any one of these 4 states. If I assign one character to each state, I can represent 4 characters. This physical state may represent A, this may represent B, C and D. You get the point. Computers are very good at working with numbers. That is why every character is assigned an integer number. We don't have to remember the numerical value for any character. It just works for us. The assignment of integer numbers to characters is based on the encoding schemes. Computers internally use encoding schemes to convert characters to integers to be stored digitally. There are two most popular and widely used encoding schemes in the world. The first one is US ASCII. ASCII stands for American Standard Code for Information Interchange. Initially, computers had to encode only 128 characters at maximum. This means that a character encoded using ASCII has a length of 7 bits. Each character is assigned a number from 0 to 128 as shown. It includes 26 alphabets of the English language, digits, special symbols, and non-printable characters like backspace, escape, or delete. Notice that there has to be a distinction between lowercase and uppercase alphabets. As computers spread globally, there was a need to encode more characters than the ASCII limit of 128. A new encoding scheme known as UTF-8 was created to fix this limitation. UTF-8 is the variable length character encoding scheme, and its length varies from 1 byte to 4 bytes. The first 128 characters in UTF-8 are identical to ASCII. This makes UTF-8 backward compatible with ASCII. Using 4 bytes, we can represent more than 4 billion characters, which is much more than all the valid characters in humankind. The input to a computer is a program. A program is any problem-solving operation that can be completed by following a set of rules expressed as instructions. Most importantly, these instructions are ordered and are executed in the same order. We wouldn't accomplish anything if instructions are executed randomly. As an example, checking whether a number is prime or not is a problem-solving activity which can be completed by following these simple instructions. Divide the given number by each number from 2 to half of the number rounded up. If the remainder is 0 in any case, then the number is not prime. There are hundreds or even thousands of programs running on a modern computer at any given time. Now, you may ask, what is an instruction? Instructions are patterns of bits that have special meaning for the microprocessor. An instruction is the smallest unit of operation a microprocessor can perform. Here I am talking about instructions at the machine level. This document details the instruction set supported by Intel 4004, the first commercially available microprocessor released in 1971. A microprocessor can support multiple types of instructions, for example, data handling and memory operations, like copy data from one location to another or set register value, etc. Arithmetic and logical operations like addition, division, subtraction, or comparing two values. Control flow operations like go to a particular memory location or call another block of code, and so on. Earlier microprocessors supported only a limited set of operations. As an example, Intel 4004 only supported 46 instructions. As technology improved, the instruction set supported by microprocessors evolved greatly. To put it into perspective, these documents list the instruction set supported by the latest generation Intel i7 and AMD microprocessors. I know, it's difficult to wrap your head around it, and you don't have to. Two important takeaways are: first, electronic circuits execute machine instructions. Machine instructions carry out the logical operations like comparison, looping, branching, etc. Second, machine instructions vary from manufacturer to manufacturer. The second point is important, as we will see in the next section. Earlier computer programs were written in lower level programming languages, which is similar to writing machine level instructions. It was very boring, tedious, and error-prone process. This has changed significantly with the release of modern programming languages. C, C++, Java, Python, JavaScript, Go are all examples of modern programming languages. These languages are higher level languages, meaning they are much closer to humans than computers. To elaborate on it, a class is the highest level of abstraction provided by the language. We can materialize human imagination in the form of a class. As an example, to materialize the physical vehicle, there can be a vehicle class. The class has properties to represent data, and methods provide actions or behaviors. Programming languages are for us. A computer only understands machine instructions. That is why programs written in programming languages are translated into machine instructions. This is the job of a compiler. The compiler takes as input a source program and outputs the corresponding machine code to be executed on a computer. If you remember, I mentioned that machine instructions are different for different CPU manufacturers. That is the reason why a compiler compiles the source code based on the target hardware. And because of the same reason, you see multiple downloadable versions of Google Chrome or any other software. Java has come through as one of the most popular programming languages in the past 20 years. The primary reason for this is Java provides an intermediate runtime between a developer program and raw physical hardware. The programmers write Java programs only once, and the program is compiled into the bytecode by the Java compiler. Bytecode is not the actual machine code but some intermediate code. Java Virtual Machine or JVM is the logical software component which acts as a bridge between the developer's program and the physical hardware. JVM takes as input the bytecode, understands the bytecode, and executes machine code instructions on the physical hardware. Next, let us focus on softwares. A program is the fundamental unit of computation in a software. A software is a set of computer programs and associated data and documentation detailing the functions and operations of the software. Think of documentation as an instruction manual for the software. Within a software, multiple programs collaborate with each other to provide us the services that we expect. Based on the purpose or domain, a software can be divided into two categories. The first category is system software. System software provides common hardware controlling functions. System software is further categorized into two categories. The first category of system software is operating system. The operating system is the root controlling software running on a computer and acts as the layer between the application programs and physical hardware. An operating system provides us the services such as memory management, networking, security, user interface, process management, and a secure runtime for application programs to execute. As an example, when I run this simple Java program, I don't have to worry about process scheduling or memory management. It just works for me. You may have used the command rm to delete a file or clear command to clear the screen. It may be surprising to know these are all programs, and like any other program, they were also written in source language, then compiled and packaged with the operating system. There are very advanced operating systems in existence today. For example, Mac OS or Windows are there for personal computers, Android or iOS are there for mobile devices, and even cars or smart televisions do have operating systems installed to control physical hardware. The second category of system software is device drivers. A device driver operates or controls a particular type of hardware attached to a computer. A hardware manufacturing company generally provides a corresponding driver for it. There are multiple device driver programs running on a computer, each responsible for a particular physical device. The operating system collaborates with multiple device drivers together to provide us the unified picture. The second category of software is application software. Application softwares are the real deal. Application softwares are designed to perform special functions beyond the normal operation of the computer. Application softwares are conceptualized based on our needs, and it can be anything. Text editor, Word, Excel, IntelliJ IDEA, Adobe Photoshop, VLC Media Player, or Chrome browser are all examples of application software. Chrome browser is an application software which accesses the internet. There is a server which responds to the browser request. That is also an application software. Putting everything together would look something like this. Lastly, let us understand program-to-program communication. Computer programs are designed to accomplish things in isolation, meaning there may be a program to book a ticket and another program for payment processing. However, the ticket booking program must communicate with the payment processing program to know the payment status before reserving a ticket for the user. We can theorize the communication between programs in several ways. For example, the program P1 can write to a file and program P2 can read from the file, or they can communicate via some external system like P1 writing to a database and P2 reading from the database, and so on. The fundamental concern with such communication is that it is not real time, meaning it is not in the moment. The ticket booking program would instantly want to know the status of payment before executing the next line of instruction for booking a ticket. This means that there should be some kind of a networking between the two which would allow real-time transfer of information. And yes, there is. With the advancements in telecommunication technologies, we were able to connect multiple computers together who were physically located at different locations. This is known as computer networking. With that, we have come to the end of this video. We will understand all about computer networks in the next video. Thank you and keep learning. I will see you in the next one.